Today we're going to find asymptotes for graphs of functions, and one that we've already dealt with before on some functions, I think, rational functions, is vertical asymptotes. In general, if you have a rational function, stuff over stuff, if the bottom becomes 0, you're dividing by 0, that creates undefined, so you have a vertical line representing the value of x that's not allowed to equal, and the graph either goes straight up or straight down as it goes towards the asymptote. All right. If you're trying to find a vertical asymptote, you set the denominator equal to 0 and solve it, and make sure the number you get that makes the bottom 0 does not also make the top equal to 0. That creates a hole in the graph, which is different, and we'll discuss that later this chapter. All right. But again, if the bottom becomes 0, that represents a candidate for the asymptote values. But then they also have to make sure the top does not equal 0. So like 5 over 0, asymptote, 17 over 0, asymptote, 0 over 0, hole. Okay? Or it could still be an asymptote, but we'd have to investigate further. All right. Horizontal asymptote is as it goes off towards negative infinity or positive infinity, where's it going? All right? And if it flattens out, we want to know where it's flattening out at. And the possibilities for horizontal asymptotes are, okay, all that matters is the highest power term. And sometimes highest power term isn't the first term, so they might rearrange the order of things. So just pay close attention, find the highest power term on top and bottom. One of three things is going to happen. All right? If you write the highest power term of each term, the top and the bottom, ignoring everything else, and reduce it, if x stays on top, there's not an asymptote. If x stays on bottom, it's y equals 0. And if x's disappear, y equals that number. Okay, and those are real easy. We're going to see all three scenarios there with examples 3, 4, and 5. And the final one is the slant asymptote, and this is for the situation of this first one, x staying on top, only if the highest power on top is exactly one bigger than the highest power on the bottom. So if you get x squared, x cubed, x fourth on top, there's not a slant asymptote either. But if there's an x to the first on top, then you're going to get a slant asymptote. And all you have to do is divide the top by the bottom. Long division. There's no synthetic division available on this one because it can be like some polynomial function, x squared, something like that. So you'll have to do long division. But it's going to be linear, so it's only going to be a two-stepper. It's going to be an easy synthetic, easy long division. But and y equals whatever the quotient is. It'll be a linear equation. Remainder doesn't count. Okay. All right, so just ignore the remainder there. So, all right. So again, depending on what they're asking you for, there's a specific procedure for each thing. Follow the procedure, get used to the procedure, get to where you don't need to look at the sheet for the procedure, and be able to do it. All right. So, example 1: find the vertical asymptote of f of x equals. So there might be more than one. There might be more than one. I don't know. We'll have to determine that by figuring it out. And the scenario here, the procedure is number 1: only focus on the bottom. What makes the bottom equal to 0? So again, if you're asked for vertical asymptotes, that's this scenario that you have to consider. What makes the bottom equal to 0? So x cubed minus 1 equals 0. If I factor that, that's going to be x minus 1 times x squared plus x plus 1. It's the difference of cubes. I do recommend factoring as opposed to just getting the 1 over and taking the cube root in case there's more than one answer. All right. The other thing, we can do the rational root theorem. You know, we know that 1's an answer, right? Yeah. So you can do synthetic division to get the reduced polynomial also. So you might not remember how to factor difference of cubes. So if you know that 1 is a factor, obviously 1 minus 1 equals 0, right? And 1x cubed, 0x squared, 0x, and 1, or minus 1, minus 1. 1 times 1 is 1, plus 0 is 1, times 1 is 1, plus 0 is 1, times 1 is 1, plus negative 1 is 0, remainder is 0, x squared plus x plus 1. All right, so again, if you don't remember how to factor difference of cubes, you still have the ability to get that second polynomial. X minus 1 equals 0 gets me x equals 1. X squared plus x plus 1 equals 0. If I did synthetic or did a quadratic formula, I'm going to get an imaginary complex answer on this one. I think it's negative 1 plus or minus negative 1/2 plus or minus the square root of 3 over 2i. That looks familiar. I think we did that one yesterday. That's why I can't remember that. But again, it's complex. Complex doesn't count for vertical asymptotes. Okay, complex means it doesn't equal 0. It can't equal 0. It won't create division by 0. All right. So x equals 1 is the equation of the vertical asymptote. So if I was to try and graph this, and this is the whole point of the vertical asymptote issue, is if you try to graph this thing, we should see that the graph has a line where it can't cross. So if I typed in x cubed divided by x cubed minus 1, and I'm going to set the window from, let's say I'll just do a zoom standard, zoom 6. There's the graph. At 1 we should see it go either straight up or straight down. It's going straight down and then it jumps across. Okay? So at 1 there is no value, but as you get closer and closer to 1 from the left it's going negative, closer and closer to 1 from the right it's going positive. Okay. Notice at 0 there's a cross, x cubed. Okay. 0, right? And cube creates that kind of bendy thing I was telling you about yesterday too there. So some of the other shaping of the graph is within that. So again, what our goal is in all this is we're going to be graphing things. So we want to get an idea of how the graph looks compared to what the function looks like to get some ideas about, you know, drawing it properly.